let's talk about the bell work. In situation number 1, says the state wants to know the average amount of left-handed people in all Indiana schools. So they survey 100 students at Pike who were chosen randomly by selecting ID numbers. What is the population of interest? Read further. Remember, population is the overall large group that we're interested in. Not the 100 students from Pike. Close. That's left-handed is what we want to know about them. What group are we interested in finding out about their left-handedness? Indiana students. Thank you, sir. The population is not necessarily who you're going to talk to. The population is where you will go to select your sample from, but the large group that you're interested in is your population. So this is all Indiana students. What is our sample then? These are the people that they actually speak to. The 100 Pike students.
Is it bias or not bias? All of them come from one school.
That's a very good question. Bias or not bias? Do you think that if our large group is all Indiana students, that 100 students from Pike would do an accurate job of representing the whole population? No. This is bias. Was there anything wrong with the way they went about selecting those 100 Pike students?
No.
There wasn't anything particularly biased in how they went about picking the students at Pike. Could you think of a way that this sample would be okay and not be biased if we had a slightly different population? Maybe if it didn't say that the state wants to know the average amount of left-handed people in all Indiana schools. Is there another way we could think of the population so that you're like, yeah, that group of 100 Pike kids would accurately represent the whole group?
Switch Indiana for Pike.
Yes. If the population was just Indiana wants to know how many left-handed students there are on average in Pike schools, selecting 100 Pike students would be a good way to do that. And randomly selecting them by student ID numbers would be an effective way of picking out a truly random sample there. So if population was just Pike students, this wouldn't be bias. In this case, the bias didn't come from how they picked the people out. The randomly selecting student ID numbers, that's a fine way to pick out a sample. But if your sample doesn't accurately represent your whole big group, it's not fair to make judgments about the whole group based on that sample. All right, number 2. To find out how all Hoosiers feel about virtual school, they randomly selected 500 citizens age 65 and older. What is the population? All Hoosiers. What is the sample?
65 and older citizens, 500.
500 of them. So 500 citizens that are 65 plus years old.
Not really an accurate representation. They have the older side of things, but not the younger side of things.
You said it's not really an accurate representation because they have only the older side of things, but not the younger side of things. So does that mean it is or is not bias?
It's bias.
It is bias.
These people worked with block scheduling and all that. We don't.
65 and older accurately represents all Hoosiers' opinions? Probably not. Even if they change that to say 500 people that all have students in high school, would that be an accurate representation of the whole population?
No.
No. What about if they only looked at parents?
No.
It'd be better, but still no. People who aren't parents might still have an opinion. Whether that opinion should be taken into account when writing public policy is an entirely different debate. But if the state wants to know what all Hoosiers think, then they need to make sure that their sample includes all the different types of Hoosiers. So they should probably talk to students also, right? Okay, yesterday we talked about sampling and bias, what we mean by a population, what a parameter is versus a statistic. Do you guys remember the difference between those two? A parameter versus a statistic? I'm going to go digging back in our books now. I'm sorry, I couldn't hear you. Yes, so the parameter is what we want to know about our whole group. Every now and then, it is possible to find a parameter. Every now and then it's possible to find a parameter. But they're very hard because you literally have to have information from every single member in the population in order to calculate a parameter. Since we don't usually have access to the entire population, we have to take a sample. And so then what we calculate from the sample, even though we're calculating what we're still interested in, it's an estimate for our parameter since we didn't get to talk to everybody. Okay. Today, we're going to revisit some of those statistics, some of those things that are calculated from samples. Whether you know it or not, you guys have already learned how to calculate quite a few statistics. Mean and median are examples of statistics. These are things that we can calculate using data. Does anybody remember what the mean of a data set is? How you find it? Yes, we're going to add and divide.
Don't you divide by the total amount of numbers there are?
Yes. In this case, since we're talking about tomato plants, how many tomato plants are there? 7 tomato plants. So we're going to find the average. Mean is the same thing as the average. So we're going to add up all the heights of the different tomato plants and we're going to divide by 7 so that we get the average height of a tomato plant here. So if you don't have a calculator on you, please go ahead and grab one because we're going to calculate this. 33 plus 24 plus 28 plus 23 plus 37 plus 29 plus 36. All over 7. That's absolutely correct. Did you have an answer for me? What do you have? 30. Yes. When you add all the numbers up in the numerator, you should get 210 so that when you go to divide it by 7, we end up with 30. We do want to label that inches. Why inches? Yes. Each of these measurements are heights of plants being measured in inches. So this is the average plant height. Average plant height. Does anybody remember what the median is? This is the number in the middle.
Luckily, it's an odd number, so you can find it directly in the middle.
There we go. Okay, so does that mean that 23 is the median? Why not? It's in the middle up here. Got to put them in order from smallest to largest first. So what's our smallest number? 23.
Then 24.
Then 24. And then 28.
Then
29.
29.
33.
36.
36. 37. And is that all of them?
Yep.
All right, so we're going to cross out until we get to the middle. So I'm going to cross out the 23 and the 37. Those are my farthest out pieces. And then I'm going to cross out the 24 and the 36. I'm going to cross out the 28 and the 33. So my middle number is what?
29.
29.
40.
Again. 29. 29 what?
Inches.
Inches again. Still plant height. 29 inches is the median plant height. Why do we have two different ways of trying to figure out what's going on with like the average or the middle? Because those numbers are pretty close together. Why don't we just pick one way of doing it and call it done? Why do we have median and mean?
Sometimes it can be very different. So.
Sometimes they can be very different. I want you guys to think about this for just a second. Your grades are calculated more like the mean, the average. We do things called weighted averages, but your grade is basically the mean. If you've gotten 70, 75, you had an 80 in there on your tests, and then you do really bad on one test, you get like a 13% on it, what happens to your grade? It goes down. And it's noticeable, right? Does that grade, after we put in that really low score, do a good job of accurately representing how you've done throughout the whole semester? No. The median is a better way to know, like, if there's consistency and then there's just like this one thing that doesn't fit the rest of the data. The median is a better way of understanding, like, oh, this is what's typical, this is what's expected here, this is about how things have been going. If you don't have that one weird test, the average is a really good way of figuring out because it helps even out the highs and the lows. But when you have a really, really low score included in there, or on the other end, a really, really high score, then the average doesn't do a very good job of telling us what's typical or what's expected. So that's why we have two different ways of calculating it here. If we calculate both of them and they're pretty close together, you're like, yeah, the average is probably a good way for us to tell what's going on. If you calculate these two and the numbers are pretty far off, then we go digging in the data to see why. So both of these are types of statistics. The last one that we're going to talk about right here is the range. What do we mean by range? What'd you say?
Maximum minus minimum.
Maximum minus minimum, yes. This tells us how spread out our data is. Tells us how far apart it is from the bottom to the top. What was the tallest plant?
37 inches.
37 inches. And the shortest plant?
23 inches.
23 inches. We're going to subtract those two to get our range.
Should be 14.
14. And would I have units with that? Inches. This is telling me there's a 14-inch difference or spread between the tallest and the shortest. Squeezing that word in there at the end. Okay. If you flip the page, we're going to continue to work with this data. Page 291 now. Up at the top of my screen, I've got the tomato plant sizes in order, like we just did to find the median. To create a box plot out of this data, we have to have what's called the 5-number summary. The 5-number summary is a statistical calculation, and we represent it visually in a box plot. It gives us a lot of information very quickly about our data set. Here are the numbers that we need for our 5-number summary. We need the minimum. What's the minimum of this data set? 23. We're going to need what's called the lower quartile, or Q1. We'll talk about that in just a moment. We need the median. This one is not on your page. I don't know why they left it out, but go ahead and add it in here in between B and C.
They left it out because we already found it.
We already found it, but we need it for this box plot, so I wish they had included it on this page. What did we say the median was? 29 inches. We're going to need the upper quartile, Q3. We'll talk about that the same time we talk about the lower quartile. And then we need the maximum. What's the maximum? 37. All right, lower quartile and upper quartile. Once we take our data and we find the median of it, we said the median of this data set was 29. The lower quartile is going to be the median of the short half of this data. So where's the short half of the data? Yep, over here, 23, 24, 28. I do not include the median in that. The median is the thing that's dividing the short half from the tall half. And I'm going to find the median of this. What's right in the middle there? 24. This is Q1, my lower quartile. So 24 inches here. I need to do something very similar for the upper quartile. The upper quartile, I'm going to look just at the taller half. What's the taller half? What numbers are included there?
33, 36, 37.
33, 36, and 37. 36 is the middle one, so that would be the median of the taller half. So this is Q3, my upper quartile. I meant to ask this on the other page, but Jimmy pointed out that we had an odd number of tomato plants. We had 7 tomato plants, and so it was really easy to find the median because it was the 4th one in from either side. What do you do if you have an even number then?
You would have to find the number in between the two.
Yes. You cross out till you get to the middle 2, You add them and divide by 2 because what you're doing is finding the average of the two that are in the middle. You would do the same thing for the lower and the upper quartiles. If the median falls in between two numbers, because we had an even number on both sides, then the lower half would include everything that's smaller than the median, including one of those numbers that you added to find the middle.
If we didn't have 37, then the upper half quartile would be 34.5 inches. If we didn't have 23, the lower quartile would be 26 inches.
That is correct. When calculating the lower and the upper quartiles, if you get to the middle of the lower half and the middle of the upper half, and there's two numbers in there, you add them and divide, just like you would do for the regular median. All right, you guys have some space down at the bottom of the page. We are going to calculate the interquartile range, and we're going to create a Box-and-Whisker plot. The interquartile range, how did we find range again? We subtracted max minus min. Quartiles, that's my Q1 and my Q3, my lower and my upper. We're going to find the range of those. So I'm going to take the bigger one minus the smaller one. What was the bigger quartile? 36 minus the smaller one, 24. So what's our interquartile range? 12 inches. All right. You guys are going to have to draw this number line down at the bottom. Here's what a box plot looks like, and here's how it uses our 5-number summary. We're going to use the lower and the upper quartiles to draw a box. So here's 24, and I've got 36 right up here. And I'm going to connect those together to make a rectangle. So again, this one right here, that's my lower quartile, Q1. This edge over here is my upper quartile, Q3. The median is going to be inside that box. Our median was at 29 inches, so I'm going to put a line in the middle of the box to show me where the median is. So that's the box part of a Box-and-Whisker plot. There's still two numbers that I haven't used yet. What have I not used yet?
Short and tall medians, so the lower and upper quartiles.
I have my lower and upper quartiles on there.
Yeah.
Those are the edges of my rectangle. What have I not used yet?
Minimum and maximum.
Minimum and maximum. These are the whiskers off either side of the box. So our minimum was 23.
I think I need an extra house.
Right here. And I'm going to connect that to the box. Sometimes it'll have just a dot, sometimes it'll have a little line. So here's my minimum. And our maximum was what again? 37. Well, that's right here. So if I see a graph of a box plot and it's trying to tell me about the data, just at a glance, from looking at that box plot, I know the smallest number. I know the biggest number. Those are the ends of the whiskers. I know where the middle is, the median, that's right in the middle of that box there. And I have this information about the lower and the upper quartiles. That interquartile range that we just found, that 12 inches, that's telling me how wide this box is. Since this is the middle of the smaller half, and this is the middle of the larger half, this right here is showing me the middle group of these tomato plants. If I want to know, how are most of my tomato plants doing? I see some short ones, I see some tall ones, but overall, what's going on with my tomato plants here? This is half of all the tomato plants. Half of all the tomato plants are somewhere in this range of heights. So the wider this box and whisker plot is, the more spread out the middle group is. When that box is very small, the middle group is pretty clustered together. All right, let's check out another situation with box plot. Flip to page 292. I've already drawn the box plot here. You guys don't have this on your page, but go ahead and copy it down into your book. You guys should have some room down at the very bottom of the page where you can copy this into your book. You'll need to draw the number line, draw the box, draw the whiskers. Thank you, Mia. They asked us to calculate something at the beginning, and then we're going to look at this picture of a box plot for the rest of the data that we want. How do I calculate the mean?
Add all 8 of the numbers together and then divide by 8.
Add all 8 of those numbers together and then divide by 8. I want to go ahead and do that.
Should equal 56.8.
All right, let me get it all written down, and I would love if somebody else could verify that for us as well. What do you get when you add them all up before we do the dividing? It takes a while to type all the numbers in. You said 56.8 when you add them all up? All right, Jimmy, you got the same thing, right?
Yep.
And we're going to divide that by 8 to find the mean, or the average. $7.1. 7.1 what?
Pounds.
Pounds.
So LBS.
LBS for pounds.
Or IBS, considering how you want to look at the L.
This is the average birth weight from this sample. Remember when we talked about the difference between a statistic and a parameter? This is a really good example. This is a statistic. 8 babies are not all the babies ever born, right? So this is a sample. This is a small group taken from the larger group of all babies. And we have now calculated this statistic. We have calculated a number that is giving us information about our sample. If I wanted the parameter, what would I need? If I wanted the parameter, what would I need to do? I'd calculate the same thing. In this case, I want to compare apples to apples, so I would still be calculating the average, but I'd calculate the average instead of just these 8 babies. I would need the birth weights of all babies. It's a lot of numbers, isn't it? This is why finding a parameter is often very difficult. I don't have access to the birth weights of all babies. Not all babies in the US, not all babies in Indiana, not even all babies in Marion County. That's still a lot of numbers. But I can get a sample of babies and I can calculate that average. And if I've picked out my sample well, I can use that then as an estimate for like, well, we're pretty sure that the average weight of most babies is around 7.1 pounds. All right, using this box plot, which again is not in your book, but I wanted you to copy it in there because we are going to read this graph and identify the 5-number summary. We know how they're finding the numbers now, but can we read this graph? According to the graph, what is the minimum? Five is our minimum, right here. Yep, that's okay. Here's my minimum, 5 pounds. On the other end, we would have the maximum. What's the maximum? 8.8. Right here is our maximum. 3 little marks back is 8.5, so this is going to be 8.8 pounds. And then we get to these pieces in the middle. We have our lower quartile, or Q1. We have our median, and we have our upper quartile, or Q3. Where is the lower quartile falling? You said what? 6.5 is right here. 6.4, because it's just one little line back from there. So here's Q1, 6.4. Where's the median? 7.35, right here. And what about the upper quartile? 7.9. Looks like it's just barely past 7.9, but reading it from the graph, that looks like that's about as close as I can get. Without calculating it myself, so just reading it from the graph, looks like 7.9 pounds. So far, so good? I think technically it's 7.95, but I'm not gonna get picky like that. If I'm asking you to read it to me from a graph, how would we go about finding the interquartile range, the IQR? How would I find the interquartile range? We're going to subtract. What numbers are we subtracting? Maximum and minimum? That would give me my range, my overall range. Range is going to be the maximum of 8.8 minus 5. So I'd have 3.3 pounds for my range. What about the interquartile range? Yep, we're going to subtract the upper and the lower quartiles. Remember, interquartile range is telling me how spread out the box part of this box and whisker plot is. So 7.9 minus 6.4, 1.5 pounds. So most babies, half of all the babies in this sample, their weights fall within 1.5 pounds of each other. If we look at all babies in this sample, there's a difference of 3.3 pounds between the smallest and the largest. But if we look at our middle group, there's not as much wiggle room there. It's only 1.5 pounds between the smallest and biggest for our middle group. Does that make sense? Let's look at one more similar to this. We're going to read another box plot. You're actually going to go to page 294. The data is on 293, but I've got the graph for 294. You have a number line down at the bottom of the previous page if you want to use it. Or no, at the bottom of this page that you can use to trace this in. Add this down for number 8. And I want you guys to practice looking at the graph and identifying this 5-number summary from the graph. What's the minimum? 2.1. In this case, it's talking about reaction time in seconds. So 2.1 seconds. What's our maximum? 8. On the upper end, our maximum is 8 seconds. Coming from here and here. What's my lower quartile? 3.25. What about the upper quartile? About 5.5. Remember, upper and lower quartiles, these are coming from the edges of the box. Here's my Q1. Here's my Q3. Where's the median?
4.45.
Right about 4.45. Right in that box. How do I find the interquartile range then? Yep, so 5.5 minus 3.25 gives us what? 2.25 seconds. Awesome. Please don't forget, you guys have one final homework assignment for me called Descriptive Statistics. It's not due until Wednesday, but it would be a good idea to go ahead and get started on it, finishing up the pieces that we worked on yesterday and today.